Hi everyone. So today is our seminar 5 and let's start it. So this is today's outline. So first I will talk about assignment 3. So I finished the grading and I will talk about assignment 4 like in the next seminar since the deadline is just like one day before the seminar. Yeah, by the way, actually, I should post this video on Wednesday, but I forgot like the date of seminar just changed. So actually I should upload this video on Wednesday, but um I thought it was on Friday. So sorry for the convenience that I caused. But anyway, I will talk about the assignment for next time. So first, I will talk about assignment 3, and then I will talk about the multiple binary variables in regression, and then like the repetition of the threads to internal validity. So the things that you should keep in mind when you write the term paper, and also some like more things, like additional things about interaction terms. And then last one is heteroscedasticity. And for multiple binary variables in regressions and threat to internal validity, we will use like to help you like use those concepts in the term paper. So we will use like one topic as an example to show you how to use those concepts in your term paper. Yes, so let's start today's seminar. So the first one is the general information, so about assignment 3. Basically, I would say that generally there is no really big problems in assignment 3. I think all of you did it quite well and gave the correct answer. But for the empirical exercise, some people just um, kind of confused with the way to calculate the standard errors. So they just put the square root in the wrong position. But other than that, I think everyone did it quite well. Yeah, honestly speaking, I think you understand the concepts quite well. I mean, like at least from the assignment 3. So yeah, everyone did quite well. And yeah, and for the general information about term papers, so all term paper drafts should be uploaded on Athena, and one per group is enough. So just as the group assignment. Yeah, so actually, how you upload the term paper is the same as like how you upload the assignments. So the only difference is that the data sets. But for the preliminary version, I mean the first draft, you don't need to upload a data set. The like the upload of data set is for your like final version. And for the presentation, you don't need to provide your presentation slides to me. You just need to how to say it? You just need to um, you just need like keep you just need to oh actually yeah I mean actually you can keep the slides to yourself, so you don't need to provide your presentation slides to us. Yeah, and for details of how the presentation will go, I I need to discuss with my um, TA partner and also a lecturer. So we will tell you how it will go. Yeah, next time I think. Yes. Um, so yeah, so these three websites are the websites that provides the tutorials for Stata. So if you would like to continue learning data on your own, you can use these three websites to learn, because actually for myself, I'm not that good at data as well, so I also need to keep learning it. So actually sometimes if you have some questions about data, I cannot answer it right away as well. So these websites are also like the websites that I will try to find the answer. Yeah, so these are three websites that I recommend to you. And then yeah, so let's enter our today's like topic. So it's just like clarification. So we know that a dummy variable or the binary variable is a regressor taking the value of one, the value 0 or 1. So 0 means no, like non-existence, and 1 means like yes and existence. So for example, if unemployed equals 1, it means that unemployed. And if unemployed equals 0, then it means that the individual is in employment. So including a dummy variable actually allows for different intercepts for male and female. So for example, like when dummy equals to 0 is, for example, like for dummy called female. So if females equals 0, it means male. So we will see the intercepts, right? And if the female is 1, so which means that the intercept for the like female equation will add the value of the difference between male and female. So this is here means that like including a dummy variable allows for different intercepts for male and female. So so you can think about that. So if we run a single variable regression, including only one dummy variable as independent variable, actually we are comparing means. So I think you understand it quite well, because actually it's the same thing in the assignment 3. So for example, you only put a dummy variable called smoke, then actually you are compare the birth weights of smoke mother with the non-smoke mother. So actually you are comparing the means. So this is one example from the college distance. So if Hispanic equals 1, then the individual is Hispanic. And if Hispanic equals 0, then the individual is non-Hispanic. And then we estimate the following equation using data. So education is the dependent variable. And then distance and Hispanic are the independent variables. So from a regression, you can see that if you are Hispanic compared to non-Hispanic, on average, you have less schooling year by 0.07 years, but it's not significant because you can see that the p-value is 0.3, which is quite big. So and then you save the predicts value for Hispanic and non-Hispanic. So it's like this. I think you are also kind of familiar with it. So you run the regression first and then generate Hispanic value and then generate the non-Hispanic value. And then this is how you graph the stored predicted values. So to graph the values, so you can use scatter or two-way. I think you also know how to do it since you do it in assignment 2. So to produce the graph for um, for the like I think it's the GDP and the trade values. So yeah, so you already used the scatter command before. So you can grab the stored predicted values. So the value of Hispanic and non-Hispanic that we just generated. And then now, so you want to expand the binary variables. So you want to make it from Hispanic and non-Hispanic to Hispanic and black and white. So now you just create more like binary variables. So you just put Hispanic and black, and you can see that now compared to white people, so you can see that the things that does not appear in the regression is the comparison group. So controlling for distance to college, Hispanic on average complete 0.2 years less education than whites, and black for 0.56, and both are significant. And you can generate this, so just as the thing that you did, just like that slice for Hispanic. And then this is the graph. So actually, when you do the dummy variables, you allow for different intercept, because you can see that. So the difference between the lines are the values that appear in front of those variables. So for example, here, Hispanic completes 0.25, 0.205 less than white, and black is for 0.56. So the difference between white, which is yellow line, and Hispanic is then 0.205. And then the difference between white and black. So the difference between the difference between yellow and green line is 0.56. So the dummy variable basically is the difference between the means of two subgroups inside your samples. So this is the thing that we would like to show you. And for the one binary variable, it's the same. So the difference between Hispanic and non-Hispanic. So this is also the value appears in front of Hispanic. So of course, this will have some omitted variables. Then you just put like more things inside your regression. So for example, you put income and the education of your fathers, and you see that it's like becomes more and more significant. So this is how we use the multiple binary variables in our regression. And then it's also related. So I think we talked about similar things before. So we can use different ways of measuring returns to education. So how this related to your topic? So because actually like they measure the same thing. So the returns to education. So which means that yeah, so we just take the returns to education as an example. So by using different ways of measuring, and if the results is similar, so which means that the statistics that you get is stable enough across like different specifications. So by like constructing different ways of measuring the same thing, actually you can make your results like more credible. And we decide to show you this example. Yeah, so we decide to use the returns to education to show how to do it. So for example, if you want to measure the different returns to education, So the first way you can do is use schooling. So you just use like years as the measurement of schooling. And from this picture, you got that the returns to one additional year is like 3% roughly. And of course, you can use a discrete variable of schooling, measuring the difference between primary, high school, and university. I think we already did it last time. So you can use like different ways of like categorize schooling. For example, if you think that the university and high school is different from each other, for example, in curriculum and also the things that they taught. So yeah, and then the third way is that you can use education level. So you can, so this is the like three, so the last one that we taught like in our last seminar is that you use three dummy variables. And here we categorize them as like three different education level. So we just make like primary as like level 1, and then high school is level 2, and university is level 3. So you can also do this, and you get that on average, a 1 unit increase in education level will increase wage by like 11.5%, so which is quite significant. So basically, like these different specification both shows that the returns to education should be positive and is stable. So yeah, so this is the third way, and also the like the way that we taught in our last seminar. So I will skip it somehow. And then yeah, so this is talking about that you can exclude certain variables to make them as a comparison group. So yeah, so this is like how we try to show that our result is stable enough across different specifications. And now we are going to show you like how we write a term paper somehow. So we will use the returns to education as example. So first, we need to define a research question. So we want to estimate the returns to schooling, and we think that using multiple binary variables is the most interesting way of measuring the effect. So we use the third way. So we just make high school, university, and primary as three like dummy variables. So this is our like simple model without any controls. So the most simple one. And you try to reason that the reason why we choose this functional form. So for example, why we put wage with log term is because the distribution of wages is skewed. So we want to make it fit into the normal distribution. So this is how you try to explain. So this is how you try to explain why you make the specification like that, and like why you and so explain that what's your question. Yeah. So the starting point of choosing the regression specification of your multiple regression model is to consider possible sources of omitted variable bias, because if we scroll back, so it's quite evident that there must be omitted variables between wage and schooling. So this is for sure. So this is called a simple model. And then you need to put your base specification, so which you are based on. So what's your interpretation and your results are based on. So now you need to think about what are the potential omitted variables between wage and schooling. So the base specification of the model should contain variables of primary interest chosen on the base of expert judgment and economic theory. So you need to justify why you put those variables in your regression. So it's not that you should you should pick up as many as variables as possible. So it's not like that. So you need to justify the reason, like you need to justify why you put the variable in your regression. Yeah. So for example, in this case, we propose three different, we propose three omitted variables. So the first one is female. So because we know that there exists gender wage gap, and also there might be some systematic difference of in the education levels between men and women because of the possible discrimination against women in work and education as well. So that's why we put female to control for the bias. And then the second is public. So like whether you are working in the public sector or private sector should influence your wage for sure. And then based on the things that you learned, so maybe it will affect the tendency for you to work in private or public sector. So that's why you put public as a control as well. And then the third one is like experience. So the years of experience, of course, will affect the wage. And then the working experience should also like have a direct effect of the length of education, because you can think about that given your wage, given your age, not wage, given your age. So if your age is fixed, like given your age, so if you have longer experience, like longer working experience, so somehow you must have lower years of schooling. Because for example, if you are only like 24 years old, and if you have like 16 years of education, then you at most you will have like 8 years of working experience, right? So this is how we justify why we put experience. And then for experience squared, it's because we think that experience is decreasing in wage. So there might exist a marginal decreasing return of the experience. So that's why we put experience squared to control for that. So this is how you justify the action of adding controls. And then, so now we estimate the following wage equation in data. So log wage I, so I stands for individual, equals beta 0 plus beta 1 high school, plus beta 2 university, plus beta 3 female, plus beta 4 public, plus beta 5 experience, plus beta 6 experience square, and the error term. So now you put them and you see the coefficients, and you can see that so all of them are significant, and also for the F statistics is 200 and 216, so which shows that like the null hypothesis is rejected. So at least one of them has impacts on wage. So you can see that controlling for other factors, the average difference in wage between high school compared to primary education has increased substantially. So you can see here. So high school students on average have 13% of wage higher than primary school, and then like 30% roughly for university students. Yeah. and f-test is 216. So which is much larger than the critical value of 2.8 for 1% significance level. So yeah, just like what I said. So which implies that there is at least one of those variables which have some impact on wages. So now you would like to do some robustness check. So because the unrestricted f-test is to ask whether all of them have no effect. But for example, now you would like to test whether the education level affects wage or not. So now you do the restricted f-test. So the null hypothesis in this case is that high school equals 0 and university equals 0. And the result shows that, so at least one of the education level matters. So this is the part actually we just did in the second part of our seminar. So to test the sensitivity of our results, I mean, on other hand, that is to test the stability of our results. So we can specify one or more alternative specifications. So for example, either you can change the way that you measure the education, so the thing that we just did, or you can also replace one of the controls with another control variable that you think might capture something similar. And the third one is that you can change the functional form. So for example, you can change experience and you can add, for example, experience qubit or other things. So here we use industry, for example, because we think industry and public capture something similar because they are both related to industrial structure. I mean, and the occupation where the individuals attend. So we replace public with industry as an alternative specification. And you can see that it actually did not affect the results of our main variable that much. So you can see that. So before, the high school is like 13%, and the university is 31%. And after we change it to industry, so it's decreased to 12.9% and then 30%. So which means that our results is stable enough. So even if we change the controls from public to industry, it does not affect the result that much. And you can see that the p-value are still smaller than the significance level of 1%. So by doing this, it increased the credibility of our specifications. So this is how we actually write a term paper. So the first is that you have a question, and then second, you give out a simple one, so the one without any controls. And then the third is that you try to find the omitted variables. You try to find the omitted variables in your regression and use them as the base specification. So the base specification is the results. It's the interpretation where you get from and also the results that you base on. And then the fourth one is you try to come up with some alternative specification to show that the results from base specification is stable enough. So, which is not just by accident or something. So it's kind of real. So then you use the alternative specification to strengthen the credibility of your regression. And then you have results and also interpretation, and then you have conclusion. So basically, this is the order of writing a term paper and how you think about like proceeding your research topic. Yeah, and yeah, now is the review. So these things are the things that you need to think about the yeah, so these are the things that you should think about the the things that you need to think about when you write the term paper, because these things will affect the credibility of your term paper. So among them, of course, the most important is about omitted variables. And I think I talked about the functional form misspecification before. And then for measurement errors and simple selections, I think these two are not that related to our research questions because they are more about the structure of data itself. So which actually not that easy to um, deal with because I think you heard term called garbage in, garbage out before. So these two things are more about the data structure. So which is not that easy to deal with when you if you use the empirical strategy. So these 3 and 4 it's not the thing that we can deal with. I mean, at least now. And then the fifth one is more interesting one. So it's called simultaneous causality. So you need to keep in mind if your research topic has this kind of problem. So simultaneous causality means that not only the X can affect Y, but also Y can affect X. So the most classic example is that, so the most classic example is, for example, the size of police and the crime rate. So not only the bigger size or of police um, can reduce the crime rate, but also the other way around. So if one area has higher crime rates, then the government will put larger size of police in that area to curb the crime rate. So when you run a regression and you found out that the coefficient in front of a police size is negative, um, oh no, it's positive. So for example, you run a regression and you found out that the coefficient in front of police size is positive. So it does not mean that if there is more police, then there will be more crime. So it might be that the causal relationship is the other way around. So it is the higher crime rates cause the existence of a bigger size of police, but it does not mean that higher I mean, like, it does not mean that like bigger police size will cause like higher crime rate. So you need to think about whether in your research question there exists like some problems like this. And if these situation happens, then they will result in the violation of conditional mean zero or conditional mean dependence and will cause the bias in your estimate. So these are things that you need to think about. And then for functional form, I think we explained the similar things already before. So this is the interaction term for um, dummies. Yeah, so I think I will not repeat it. Yeah, and then the last one is about the heteroscedasticity. So we know that the classic assumption for OLS, ordinary least squares, is the is the error terms, the distribution of residuals should be homoscedastic. So the residuals should not be related to any independent variables. But of course, we know that it's not that easy to hold in reality. So you can see that. So the upper one is the heteroscedasticity. So you can see that as long as the value of independent variable increase, the variance of residual just becomes larger and larger. And the lower one is the homoscedastic. So you can see that the residuals does not actually has no relationship with the value of independent variable. So it's just like more like random. So if we have the heteroscedastic errors, then the standard error that we estimate in our regression tends to be wrong because we use the wrong assumption. So in reality, the assumption of homoscedasticity is unlikely to hold. So if you use the homoscedasticity formula to estimate standard errors, will give us a wrong standard errors. So the coefficient itself is right, but the standard errors are wrong. So what's the problem? I mean, yeah, the estimates are right. So what's the problem? So the problem is that because we use standard errors to calculate the t statistics and p-values. So if your standard errors are wrong, which means that it will give you wrong t statistic and also p-value. So it will also give you wrong inference. So if you use homoscedasticity formula to estimate a heteroscedasticity thing, then the value, so for example, something might not be significant in reality, but since you use the wrong assumption, then you get the significant result, but actually that one is wrong. So how we correct the problem is that, so actually the way to correct this problem is quite straightforward. In Stata. So you just put a term called robust at the end of the regression. Then you can calculate the heteroscedasticity consistent standard errors. So I would recommend you to use heteroscedasticity, like put robust after your regression always. I mean, even in your term paper, because in reality, like the assumption of heteroscedasticity is much more likely to hold compared to homoscedasticity. So using the assumption of heteroscedasticity is always a safer option. Yeah. So as a robustness check, yeah, so this is also one way of robustness check. So you can present a table from a regression assuming homoscedasticity and also heteroscedasticity, and to compare the t values and so p values. Since we know that t statistics and p values depend on how your assumptions change. So if you see that the standard errors, so if you see that the t values and p values actually roughly the same, so which means that the error terms from your calculation is actually homoscedasticity. Yeah. So this is about heteroscedasticity and homoscedasticity. So the last one that I want to show you is that how you can produce the tables in your regressions. So you use SOUT in Stata. So you need like additional packages to do that. So how you install SL is to use this command. So use SSC install and sdout replace. So then you can install this package in your regression, no, in Stata. And then, for example, now you want to record the result of your regression. Then first you run a regression, and then you put like add local HC robust no. So which means that when you add this, so this is also one of the command inside the sout command. So which means that to add some more like specifications. So this one is to show that you add the results without putting robust. So this one is like yes, so which means that you put the things with robust. And then you want to store them. So you put est store whole and then est store he. So which means that now the result of this regression is stored in the variable called whole. And the results with robust is stored in a variable called he. And then the next one is that then you use the est tab to document these two variables, whole and he. And then these are the other things that you would like to put in your regression. So it's like stats. So it's the statistics. And then SE stands for standard error, and star stands for the significance level. And by doing this, then you can get this format. So if you want to store the table in the form of Word file, then you can use the using table RTF. Then this table RTF, this Word file, will appear in your working directory. So this is how we produce the table that you saw in the paper. So we use the sout, this package, to produce these tables. Yeah, so this is the seminar today. Yeah, and see you next time.